So everything we've been discussing about solo is captured here in this single XY plot showing the output current and output voltage. In this plot, you can see the large orbits and the smaller orbits along the curve. Time is not shown, this is just an XY plot, but basically this is T0. We do a large orbit scan. We circle around the operating point till we jump out here and we find the solution. This solution from the large orbit scan is now handed to the small orbit controller, and the small orbit controller starts doing these small little deviations. These are really little figure-8 orbits all along the power curve shown here. This power curve is constant power, 41, 42 watts, which would be the input from the solar array. You can compute the product of the current and voltage along this baseline anywhere along here, and it'll be 41 to 42 watts. We're using 100% efficiency for the converter, which I know is not realistic for a real system, but in our model we're not concerned with the efficiency of the converter. We're just trying to make our control circuit and control loops function. So we're using 100% efficiency, 42 watts, 41 watts on the array is delivered completely to the load as shown here. So this is the essence of solo. You have your small orbits, your large orbits, and that's really the whole technique. So if you're still watching these videos, that means you're somewhat interested in the solo technique. Hopefully today's description of the large orbit and small orbit waveforms will help you understand it a little better. Part 6, I will go through the waveforms, timing diagrams, and circuits used to make this control system, and hopefully we can wrap it all up. Thank you for sticking with it this far.